Okay, so we have the second talk of this morning session by Tariq Osman about tales of generalized theta functions.
Thank you for the introduction, sorry. And also, thanks to the organizers for the invitation to speak. It's been very nice meeting all of you. Also, special thanks to Marco and Francesco for inviting me to Bologna. Before I came here, I don't think I would have been able to come if it weren't for that visit. So thanks very much. Oh, and also thanks to the Riemann Institute for hosting us in this very nice location. Okay, so today I want to tell you about the tales of generalized theta sums. So Francesco explained to you what those are, but I suppose for the sake of completeness, I should tell you what they are again. So they're just exponential sums, right, of a particular form. So where's the pointer? So we have some special weight function, which we sample at a rate of 1 over capital N. We multiply that thing that we've sampled by some phase, which is e to the 2 pi I of 1/2 n squared x, n squared plus beta n, all times x, plus n alpha. And then we sum over the integers, okay? The sum is the sum part. All right, and these are well-studied objects, as Francesco mentioned. They appear in the works of Hardy and Littlewood, Flaminio and Forney, Berry and Goldberg, and also in the works of Jens Markloff and Francesco, and I suppose now myself. So they're well studied. People are very interested in them, either from physical points of view, but I like to think of them as purely number theoretical objects sometimes because the physical way of thinking can be overwhelming. So what can I think about? Well, we want to ask ourselves a simple question. So suppose alpha and beta are both fixed real numbers, okay? And suppose I choose x to be random from the unit interval, 0, 1. Okay, and I choose it with respect to Lebesgue measure. Okay, nothing fancy. Then I can think of this sum as a deterministic path in the complex plane, but with a random seed. So I've randomly chosen x, but after I randomly choose x, it's just a deterministic thing, right? Because alpha and beta are fixed real numbers, and then we can ask ourselves, well, what's the probability that this path, if I normalize it appropriately, is going to exceed a ball of large radius. All right? So that's my simple question. And I'll try to answer that question at least in some part today. So if you started with alpha and beta where at least one of them was irrational, then Cialrossi and Markov have an answer for you, or at least a partial answer, which is that if my initial weight function is Schwartz, right, then the probability that my generalized theta sum, when I normalize by square root of n, in the limit as n goes to infinity is large, is asymptotic to 2 over pi squared times some special constant that depends on f, the weight function you started with, times r to the minus 6. So as r goes to infinity, okay? So this means, in particular, that if you can prove that there is a limiting distribution for sums of this type when normalized by root n, then the limiting distribution couldn't be a Gaussian to begin with, right? Why is that? Well, the Gaussian distribution possesses all of its moments and is determined by its moments. But here we only have finitely many moments, as Francesco mentioned, right? There's only 6 minus epsilon moments here. So what else should I mention before I move on? The interesting thing is that this constant that we have is universal in the sense that it doesn't depend on the alpha and beta that I started with. It could be any alpha and beta square root of 2 and 1, maybe pi and 0, and you always get this asymptotic, right? The only dependence that you have is on the specific weight function that you started with. I should also mention that in their work, you can choose f to even be slightly less regular functions than Schwartz functions. You could even choose it to be a sharp cutoff, in which case you would get this constant here to be 3. Yeah, so that you get 6 over pi squared. Okay, fine. Oh, sorry. So what if now I choose alpha and beta to be both rational? Well, the surprise is already spoiled, so I'll just dive right into it. So it says that if I choose my rational numbers, alpha and beta, to be of a particular type, so of the type a over 2m and b over 2m, where a, b, and m are all odd and have GCD equal to 1, right? The GCD condition is just to get rid of some degeneracies in these things. Then the limiting distribution is compactly supported. So in particular, it means that once I choose my radius large enough, my normalized sum will never exceed that radius. It stays bound. That's quite nice, right? And somewhat surprising, and in stark contrast to what we saw in the irrational case, which we have very heavy tails. I should also mention that it also means that the limiting distribution for the sum is, again, not Gaussian because the moments don't agree, but for an entirely different reason, right? Here we still have all our moments, but they, again, just don't agree with the Gaussian. So it can't be the normal distribution that you have. And for all other rationals, the probability as n goes to infinity that my normalized sum exceeds a ball of large radius is asymptotic to some constant times, so a constant that depends on alpha and beta, times another constant that depends on f, which is distinct from the constant in the irrational case, now with a heavier tail. So the way it depends on r is r to the minus 4 as r goes to infinity, as opposed to before in the irrational case, we have, as r went to infinity, the asymptotic was r to the minus 6. Okay? So the tails are now heavier in all of these other cases once you don't choose them to be of this type, right? So it's truly distinct from the irrational case. And there's no universality in the choice of alpha and beta. However, if I did choose my sampling measure to be something absolutely continuous with respect to the Lebesgue measure, and I choose x random in all of r according to that measure, then I would still get this asymptotic. So there's no dependence on the sampling measure in this setting, right? The only dependence is on alpha and beta and f, okay? And oh, I think I forgot to mention in this slide, the f that I'm choosing is again Schwartz, right? I could also change it to be the indicator of the unit interval, let's say, but that would make the talk, I think, too technical. So I won't do that at all today. Okay, so my goal is then to tell you about how you get these asymptotics. All right. So as Francesco mentioned, there's some special function, right? I'll call it capital C. And it lives on a special group, SL2R semidirect R2. Some people call that ASL2R, right? And this special function is invariant under a certain discrete subgroup. I don't really care about what the discrete subgroup is, but it's discrete. And when I quotient by it, it gives me some finite volume quotient, right? That's the most crucial part. I should also mention that using the Iwasawa decomposition of SL2R, I can put a correspondence between SL2R and the upper half plane times the interval 0 to pi. In other words, the unit tangent bundle of the upper half plane times R2. The times R2 part doesn't come from the Iwasawa decomposition, that just comes from the semi-direct product over there, right? And so with this identification also comes an action of the group G on the upper half plane, the unit tangent bundle of the upper half plane times R2, right? So through the identification, I have an action, and so I can quotient this space by that action. In other words, I identify points up to, say, their G equivalents. So in this case, I want to identify points up to their gamma equivalents, and that'll give me some fundamental domain. So here's a picture of my fundamental domain. Okay, it's really just, if you're familiar, it's just or a fundamental domain for the theta subgroup times the interval 0 to pi. And then I tack on a torus over here. And that just comes from the quotient coming from R2. Okay? So this is just a fundamental domain for the action. Go ahead. Oh, sorry, the picture is kind of bad.
I was just asking about the generators of gamma theta.
Yeah, sure. So this guy is generated by 1, 2, 0, 1, and 0, minus 1, 1, 0. And it's an index 3 subgroup in SL2, right? Okay. Maybe the more usual fundamental domain that people are used to seeing is this one here, but I've chopped that piece to bring it over here, so I have two cusps rather than half a piece of a cusp over here and half over here. Okay. So far so good. I see on the projector, can't see the square that I've drawn in, but I guess it doesn't matter so much. So it's a very poor square. And my picture is better here, but okay, I hope that's clear enough. And the shading is okay in the projector, so okay. So hopefully it's clear that it's thickened by an interval of 2 pi in this direction. Okay, so what next? So this special function that lives on this fundamental domain, we can use that function to write out our normalized theta sum. Okay, how do I do that? Well, Francesco showed some kind of computation, but you can think of this thing here as sort of like your geodesic flow. And this guy here is your horizontal flow, or some lift of it, right? And so using this flow and this flow, I can write the normalized theta sum. There should be a weight function f up here, normalized by root n, in terms of this special function c as some group element or some coset times a horocycle times the geodesic. Okay? So why is this significant? Well, I'll say in a second, but you also saw some kind of computation that convinced you that, well, the x dependence here is sort of annoying. So I can get rid of it using some tricks of the group action and pick up an element over here that is n and x dependent, beta dependent, right? But that element will go to 0 and the limit as n goes to infinity. So morally by 0, I mean it will go to the identity as n goes to infinity. So in the sense of the limiting distribution, it doesn't matter. It goes away, and I can just consider expressions of this type, right? Okay, so the point is that the limiting distribution of my normalized theta sum is related to the limiting distribution, is the same as the limiting distribution of the special function c sub f evaluated at a certain point, right? Along a horocycle at a certain geodesic height. So if I ignore the alpha and beta for a second, right? And I just look at what's going on in the SL2 part, we know exactly what happens dynamically, right? We have some non-compact finite volume quotient of SL2R, right? And I usually attribute this theorem to Sarnak, but I don't know if the ineffective case was proved by somebody before him, or maybe it was Foucault up until that point. And I'll just use the ineffective version today anyway. But it tells us that probability measures supported on curves corresponding to this in your quotient of SL2R by some discrete subgroup converges to the normalized Haar measure as t goes to infinity. So what I'm trying to say is that here's a little picture to illustrate. So I have gamma prime, my quotienting subgroup, to be SL2Z, right? And I can draw in what this curve is supposed to look like. It's supposed to just be some horizontal line like so, right? And I want to understand what this curve looks like in the shaded region up here, right? So I use the gamma prime action to bring the segments of the curve back. So let's say I have this segment of the curve, I want to bring it in using some element gamma in gamma prime. Okay, so it brings it into there. Maybe I get this segment here, for instance. All right. And as I take this thing, the height of this curve is determined by t. And as t goes to infinity, it pushes it further and further down into the boundary. So as t goes to infinity, the height of this curve goes down, right? And even if you've never seen this sort of thing before, it's not hard to believe that in the limit as t goes to infinity, you get something that's equidistributed, because this tessellation gets more and more fractal toward the boundary. So I'm just translating, more and more pieces into this thing. So here are 3 different pictures of what can happen as t goes to infinity. And in the limit, you get some normalized thing. So that's a Haar measure. It's really supposed to be a graded picture because you have a weight of y squared. But you get the idea, right? Okay, so far so good. And then from here, we want to reintroduce our extra element, alpha beta. So the part in the R2 component, right? So I'll draw in my square again, sorry, because it's not showing up on the projector. Okay, so very ugly square. And so what's going to happen this time? So let's take a horocycle again. Okay, and think of this as on the face. So when phi is equal to 0, so the angle here is corresponding to 0 in the unitangent bundle. And you have some tessellation afforded to you by your quotienting subgroup over on this side and also over on this side. All right? I want to take a point on this curve, and this track what happens. So I'll pick this point here, and that means if alpha and beta is fixed, then I should pick some point here. Okay? So now I want to move this point back into my fundamental domain, so I have to use the action of gamma. But gamma is going to act on this entire thing. So in particular, it's going to affect not just the segment of the curve that lies in some gamma translate or gamma prime translate, but gamma prime is just the SL2 part of your subgroup, so back into the fundamental domain, but it's going to affect this point as well. So it's going to, you translate your segment in using some gamma, so you get some piece of a curve like that. And that curve may go through different angles, so you should also keep track of that in the unit tangent bundle. But it's also going to force this point to jump to something else, right? But if alpha and beta were rational to begin with, then I'm only going to get finitely many points. So maybe that's my orbit, right? Then you have to do some extra argument to say, well, do I actually get the entire orbit? And is it the uniform orbit? Is it a measure that's uniform on the orbit? But you can do some kind of argument and you get this. So great. So you have now a limit theorem which tells you that if I start with alpha and beta rational, then the probability measure supported on this curve corresponding to this, right? So you're pushing forward some measure that's absolutely continuous with respect to the Lebesgue measure onto this curve. Then those measures in weak star are going to converge to a special measure, d mu alpha beta. That measure is just the Haar measure over here, right? Or Haar measure on the quotient, times a uniform measure supported on finitely many points, right? So great. So I want to use this limit theorem to understand the limiting distribution of my sum. So that limit theorem that I just talked about, plus an approximation theorem which has to deal with, if I go back a couple slides, has to deal with this G and beta, which you just have to do some relatively standard things, but not really very exciting things. You get this limit theorem, which tells you that for nice enough sets, so nice in the sense that the boundary has measure 0 according to the limiting measure, whatever, that the probability as n goes to infinity that your normalized sum lands in this nice set A converges to the push forward of your mu alpha beta measure by this weird function C sub f, right? Okay. So now I want to choose, because remember at the very beginning I was talking about tails of these things. So now I want to choose A to be the interval r infinity. So the complement of a ball of radius r, because this is a real valued function. Okay. So I plug that in and I get this expression, right? It's exactly this expression. I just rewritten it over here and simplified the notation of it. Okay? So what happened? So now I want to estimate. So let's forget about the whole limit thing and we just study this, the measure of this set according to the mu alpha beta measure. So I have my fundamental domain and I'll split it into two pieces. So again, I have a square here and another square here. This is a unit square. I call one piece f infinity and one piece f1. The infinity just has to do with because you have a cusp at infinity, and the 1 has to do because you have a cusp at 1. Okay, fine. And these, you can set them up so that they're disjoint. So the measure of the set of things where your theta function is large, according to the mu alpha beta measure, is just going to split into two pieces. Right? Nice. And so I'll just study one of them, and I'll choose this one for convenience. Okay, so let's study that. To estimate this thing, I first need to define something for you, but it's just notation. Okay, so I'm not really going to define what the phi transform of f is, but when I write f sub phi, what I really mean is that it is some special transform of f that is something like the Fourier transform. So maybe there's some extra rotation phase in your integration kernel, but morally it is like the Fourier transform. Some people refer to it as the fractional Fourier transform, I think, in applied circles, and they study it in the context of optics and that sort of thing. But, okay, whatever, you have some integral transform. And this integral transform of your initial weight function f is related to your C sub f in a special way. It tells you that if once I choose my point that in a fundamental domain such that y is greater than 1/2, right? And I write little theta to be the fractional part of the second coordinate of my initial vector, yeah? Then I can approximate my theta function using this phi transform in a particular way. It's just y to the 1/4 times the modulus of f sub phi evaluated at minus the fractional part of the second coordinate times the square root of y. And you pick up some derivative. Okay, fine. The reason this comes up is because the phi transform is really intimately connected with the definition of this special function C sub f, right? And the estimate just comes out if you do the triangle inequality. This thing gives you the main term, and then the rest of the things you just bound in the error term. I should also point out that I think I forgot to say eta has to be strictly bigger than 1. You cannot take eta equal to 1 in this thing. It's very bad because the constant is essentially the zeta function evaluated at eta, so you do not want the zeta function at 1, right? So using this lemma, it's sort of convincing, maybe not entirely convincing, that the measure of the set of things in this piece of the fundamental domain that I brought out that only contains the cusp at infinity, such that my C function is large, is roughly, not quite, but roughly the set of points in my fundamental domain such that this expression here is large. All right, so this drastically reduces the problem because at least we see some explicit dependence on f, right? With the function C sub f, everything is very mysterious. This is still somewhat mysterious because I didn't really say what the phi transform is. Francesco did mention what the phi transform is to some extent, but you know, at least you see something. So I can then write exactly what this is as an integral, right? This sum just arises because, remember, this thing here was the Haar measure on one side times a bunch of delta masses. So I have to evaluate theta at the second coordinate of the vectors in the orbit. Okay, so I have some integral. Okay, fine. And here's where the trick happens, is that because you started with a Schwartz function, it turns out that the phi transform of a Schwartz function is also going to be Schwartz. So this expression here has to be bounded, right? Because you get nice decay in the parameter of your phi, f sub phis, right? So once I choose R to be big enough, this set here has to be empty, because there's not going to be any y that guarantees this to happen once R is big enough, right? Sorry, and that's in the case when theta is equal to 0, is not equal to 0, right? So I have some non-zero theta. This thing here is always going to be bounded, because this thing has enough, the phi transform has enough decay to compete with the y to the 1/4. All right? So, right, so this thing is empty, but in the case when theta is 0, then the input there is O of 1. In fact, the input here is 0, and then you're multiplying some constant by y to the 1/4, so you must have growth there. Okay? So the only contributing terms in this integral are the vectors, the situation where this theta is in fact 0. So all that's going to matter is the points in my orbit where the second coordinate is 0. So this integral that I wrote on the previous board here, I don't have to care about the sum at all. I just multiply it by a factor of s infinity, where s infinity is the number of points such that the second coordinate of the points in my orbit have a 0 in the second coordinate. Sorry. Okay? All right, so now I just do this integral. And then it just becomes morally an exercise. The 2 comes, there's no x dependence in this thing, so the 2 comes out, right? And there is some phi dependence in the definition of the set, so you have to be careful with that. There's a y to the -2 there, so you do this integral. Okay, fine, and you get this clean expression. So immediately you see the y, the r to the -4 as claimed. You see some constant that depends on f as claimed, and some constant that depends on alpha and beta only as claimed. Okay, so in summary to all of that, all I tried to say was there is some, this set here, the set of things in f infinity where my c function is large, is this blue region. You have to be up in the cusp and close to this band, right? But if you have a discrete set of points, you literally have to be on this line, right? And so the only contributing factors to this integral, if I compute the mu alpha beta measure of this thing, this region, according to the Haar measure, times the number of points sitting specifically on that line. Sorry, the picture is kind of bad, but maybe I'll just leave it, because Francesco showed you very nice pictures a little while ago. Okay, so you get this asymptotic. So, all right, and then we have that F1 thing to do, so we just do that all over again. That just comes from a change of coordinates, because I want to flip this region. So I want to apply this lemma again. I should have put it a second time, but in this lemma, y had to be strictly greater than, well, it has to be strictly positive. Though greater than 1/2 is not really that important, but it has to be bounded away from the boundary. So you need to do a change of coordinates so that you can apply that lemma. And when you do that change of coordinates, this band here is what gets mapped close to the line of things where the second coordinate is 0, using that change of coordinates. And so I get, if you do all of that and you compute that integral, you get this asymptotic for this piece. Okay, So now you have two asymptotics for the disjoint pieces of your initial fundamental domain. And we add everything up. So the mu alpha beta measure of the set of things where my theta function is, my C function is large, is asymptotic to some special constant that depends only on alpha and beta, some special constant that depends only on f, and this is what we called d right at the very beginning. Sorry, and I think I should put the pi squared also with this. Where's the eraser? Okay, and this pi squared also goes along with this. And then I had some special constant that depends, that's my C alpha beta that I had in the beginning. And I have this r to the minus 4. Okay? And then from there you can compute what S infinity is, S1 is, and S, right? In every case of alpha and beta that you give me. And you can do some lengthy computation and consider all the different parity cases, and you get some explicit formula for all the C alpha beta. Remember, C alpha beta is the thing without the pi squared. That's my C alpha beta. And this special psi function is the so-called Dedekind psi function. Okay. And so that's all I wanted to tell you. So thanks for your attention. Thank you.